I'm Mike Parowski from the Network Threat Detection team at Meta, and my co-presenter here is Sam Manzer on the Purple team. And over the last few months, we've been fusing our defensive and offensive skill sets to build an end-to-end automated offensive attack framework that enables us to validate and tune our detections. And so we're here today to talk to you about that process, some of the challenges along the way, and the successes we're seeing as a result. So just to do a little bit of bookkeeping first, I'm going to first introduce you to my team's hypothesis and kind of reason for existing and what we're working on. And then I'm going to hand it off to Sam to defend that thesis. And then we're going to dive into the process of detection engineering on our team, how Sam's attacker on demand infrastructure helps us achieve those ends, and then sort of walk you through what it actually looks like to use this system and how it enables us to build highly effective, high fidelity, proactive detections. So first, the thesis, and I do anticipate some eye rolls here. So these days, it seems most industry standard detection and response strategies rely very heavily on application logging and host level logging as a first line of defense, only then pivoting to network telemetry to gather additional context and evidence. My team's hypothesis is that this paradigm is backwards, that we can actually rely on network telemetry first, as it is inherently reliable, comprehensive, and generalizable. And we're going to dive into more about what that means, but I just want you to keep that in mind as we talk through it and be the judge of it yourselves. Cool. Sam?
Hi there, y'all. So let's talk a little bit about these network level detections and how they relate to EDR, that sort of table stakes endpoint host-based protection that you got in your organization, whether it's from Microsoft Defender, or CrowdStrike, or whatever y'all like to use. So EDR is pretty good these days. EDR will generally make your life a lot more difficult if you're a red team or offensive practitioner of some sort. You can get around it, but it gets harder and harder every year. And it's pretty smart at catching the obvious stuff these days. So nonetheless, I want to talk a little bit about how network level detections can provide a lot of additional value and really complement the organization's security strategy. So the challenge with EDR is that there are a whole bunch of ways to trick users into disabling it. This is my favorite one. So if you go on GitHub and you go use whatever cool new JavaScript framework or new tool, a lot of them will tell you to do this, and in fact, to install the product. And in fact, some of the security products out there will also tell you to do it this way. And this will basically bypass a lot of EDRs because it never hits the disk, because you already elevated to sudo. So if you want to try something fun, you can just put a little shell script in there, and they wouldn't let us put in the exact one-liner for this, but you can ask me after the talk. Can disable a lot of interesting EDRs just with this. Couple lines, drop a commodity payload that any EDR should catch, won't get caught. And so I think this sort of little tidbit is sort of an example of the general class of issues that relying solely on EDR can give you, which is that it's fragile. It's on the endpoint. The employee has access to the endpoint, and if they have sudo and they're really busy, there's a whole bunch of stuff they can do that's going to remove that layer of protection for you. The other challenge is that if you're in a big organization, you probably have a whole lot of different kinds of endpoints, and they may not all have EDR. And even if they do, EDR may not work the same and to the same level of quality and protection on one type of endpoint as it does on the others. So because of the fact that EDR exists in this hostile environment where you got users who are always just like one right click away from doing like run as administrator or what have you, or otherwise somehow bypassing your protections, it can perform well in certain scenarios, but in other scenarios it will struggle. So let's talk about how well EDR can work in different scenarios within the organization. So I like to think of Bob as sort of like the role that EDR is really best designed to protect. So you know, I bet a lot of y'all, if y'all worked any kind of IT support role in the past, you think like, oh, well, Bob's are the source of a lot of my problems. Bob's always trying to upgrade Adobe Flash Player, and it causes me all kinds of problems. And that's true. No one can completely protect the Bobs out there. But EDR does a good job of catching a lot of the type of stuff that Bob is going to click to get your endpoint owned. But the challenge is there's a whole lot of other kinds of endpoints and a whole lot of other kind of workflows out there. So your devs, for example, probably using Macs in a lot of shops. That's okay. Your EDR says they support Mac, but the actual performance of a lot of the detections may be drastically different than what you'll see on your Windows fleet, for example. In addition, the devs are probably more likely to be the folks who are going to curl to bash with sudo. And so they have a sort of unique set of threats that come from those types of workloads. Now, we've also got folks doing really high-end R&D work, and the machines that they're running, which will probably look a whole lot different. Maybe they don't even have EDR at all on them because someone forgot to set that up. Or maybe, again, the EDR doesn't work well because they're weird BSD machines or something like that. So it doesn't stop there, right? Your Docker container is also an endpoint. If you get supply chain attacked and you get some evil NPM package that drops an implant inside that Docker container, well, it's contained in a certain sense. Can probably scan your whole internal network though. And there's probably like a whole bunch of other nasty stuff it can do too. If you're running some EDR on a MacBook and you're running Docker for Mac, which is a Linux VM inside, almost guarantee you it's not getting scanned at all. So there's some challenges there. And then of course, there's every single other kind of device that's running behind your perimeter. Could be a switch, could be the CEO's Apple Watch, all kinds of stuff. This wide variety of different endpoint types and the challenges in getting uniform EDR coverage across that leads to a situation where network threat detection can especially shine as a complement that gives you that breadth of coverage. And so Mike is going to tell you a lot about how we get a lot of value out of that.
Thanks, Sam, for the good info and justifying my employment. I appreciate both of those always. So as he mentioned, yeah, and as you can see in the diagram here, what we are really proud of is the fact that as long as you intelligently select where you are tapping the traffic and you ensure that you're utilizing very natural choke points that we expect everything to flow through, we will see it all in the network, independent of device or operating system or newness to the network or what have you. And so we leverage this advantage and attempt to detect these three TTPs mainly. We are exclusive, or not exclusive, we are mostly targeting command and control traffic, anomalous data exfiltration patterns, and network service discovery or mass scanning inside and around our network. And we do this using mostly Zeek logs. So for those of you who aren't familiar, Zeek, which is formerly known as Bro, is an open source and passive network analyzer. I like to think of it as a connection-oriented Wireshark. So rather than inspecting individual packets, you're seeing the full session between any given set of endpoints. What we really like about this is it formats our logs in a highly digestible way. So just right out of the box, we can ingest them into our internal data systems and query them intelligently and build our detections around that. Additionally, it's very extensible. So while it comes with a series of base packages that we rely on pretty heavily, we can add things onto it over time as we have new protocols being introduced or new detection methods that we would like to try out and look out for in our network. So to use this software, we own and operate a fleet of sensors, and we position them all along the perimeter of our enterprise network. And what this achieves for us is this natural choke point that I mentioned before, where all traffic egressing and ingressing our corporate environment into and out of prod we see, and into and out of the public internet we see. In addition, inter-DC hops within the enterprise network we also catch. So what we have here again are these natural choke points, these locations around our network where we are virtually guaranteed to see all traffic go in and out of, independent of where it's coming from and the platforms it originates from. And so we can use sort of this advantage to build really high fidelity detections on top of, assuming we can overcome some of the challenges that we're going to discuss. But before I get there, I did just want to give you a little bit of an example before we get too deep into the weeds. This is what your typical Zeek log will look like. So this is the DNS.log, which we use pretty heavily for DNSC2 detections. And as you can see here, you get the basic fields that you would in any sort of NetFlow with the source IP, dest IP, and the ports. But you also get all of the very specific DNS fields parsed out completely in a very queryable way. So you have the actual query name and the class and the queue type and so on and so forth. And so these are the fields that we can sort of intelligently pick which ones are relevant to map after attacker behavior and sort of model the behavioral detection around. And so the reason I showed DNS first is because this was actually the first success that my team had inside of our network. So we were monitoring for anomalous spikes in DNS text queries, which is sort of the canonical network telemetry as a detection source example. In case you're not familiar, DNS text queries enable arbitrary blob data to be communicated back and forth, and it's difficult to block because you would essentially have to disable DNS across the network, which breaks a lot of things or everything. So we took this concept, began modeling what the DNS text queries look like in our environment, and set some thresholds. We wanted to see when there were really large spikes in that behavior and alert when we see them. And so this was the first big win that we had that came out of that. As you can see here, we had a task generated with all of these really fun looking domains that at first glance look scary, like there's a ton of important encoded data being transmitted across, but also with these very fun dictionary mashed up words like beneficial skullcap and life in the DMZ, which seems a bit conspicuous for your standard attacker. So I went ahead and tapped the shoulders of our offensive security group at Meta, and sure enough, this was a covert red team op, and they were exfilling some data and using DNS text records as a way to command and control. So after this victory, we started to feel quite confident that, okay, we can use this network telemetry and develop pretty high fidelity detections after it. And now I do just want to nip this one in the bud because we get this all the time, and I feel like I'm constantly addressing this. So right out of the gate, yes, network detection is hard because a lot of things are encrypted. However, this should not be a reason to not use network telemetry and build a detection system on top of that data. It often gets cited as, well, if everything's encrypted, how much value can we really get out of it? I'm here to tell you a lot. There's a lot you can do with this data because there are a bunch of remaining unencrypted protocols, some that will surprise you, which is Signal on its own. And then you can also use the metadata, even in encrypted traffic, to get some pretty interesting results. For example, time series heuristics, which we are going to dive into next, is what we're using for some pretty cool C2 type beaconing detectors. So before I explain that, I just want to show you, this is the SSL log. It's just a legacy name, but it encapsulates modern TLS traffic as well. This is the default Zeek log for SSL traffic. Same thing, you get the standard NetFlow traffic plus some of the algorithms used, the server name, cert chains, and so on and so forth. And so my job in this detection, this specific detector we're going to talk about, was to identify which fields here we could use, even in the case of an encrypted C2 traffic. And so really all we needed was the flow traffic, the timestamps, and then some of the server name and endpoint information, which we can all get pretty easily here regardless of the encryption used. So to go forward, I'm going to lay out sort of the scenario that we're working with here. So Sam Manzer, a very honest and hardworking employee at Meta, saw this email and felt the absolute need to click it. And as a result, now has a little implant installed in his machine that is going to be communicating out to the attacker infrastructure using SSL as its C2 transportation lane. A common tactic with these C2 frameworks is to include a repetitive, a periodic beaconing function, essentially a still alive, to communicate out to say we still have this foothold, and give the attackers the peace of mind that they continue with their operation at their leisure. There's some nuances to it. You can introduce jitter in either direction, but essentially what you're going to be looking at is traffic that looks something like this, just very periodic spikes in traffic to some location. It's not going to be a lot of data being sent, but it's going to be very patterned. This deviates, in theory, pretty significantly from standard traffic going on inside of the corporate environment. So our logic is, okay, let's try to encapsulate this behavior in a little SQL query, target our SSL logs, and see what we can find. And so that is exactly what we did, and we uncovered a few different, pretty significant challenges. The first one here is that large corporate networks, particularly the one that I've been working on, are very loud. There is a ton of noise in every direction, and for every detection idea, however rock solid it might be, you're going to have dozens of corner cases and edge cases for every engineer you could possibly think of, saying that they need this tunnel exiting the network and egressing all of this data, which drives me crazy, but we have to acquiesce sometimes. So that's the first challenge we run into. The second one is you can put all your effort into developing these really intense, logically sound queries, and you end up with something that looks like this, albeit obfuscated SQL code. But the problem really comes around when you can dedicate all of these resources, but you have no idea that it's actually correctly targeting what you want. You could be getting 100 results per day, but how do you know that the actual beaconing traffic that you're looking for is in those results every day? So that's a problem we're trying to address. And then this last challenge that I want to discuss is something that should be familiar to pretty much everyone in the room here as security professionals, although I do feel that in detection engineering, it is particularly front of mind, and it's that we are all constantly trying to prove a negative. If our detections don't fire, it means there was no attack, or was there? We're sort of always waiting to justify our existence by saying, hey, look what we probably most likely stopped. Here's the proof that this thing happened out in the wild and we have defense there. But if we don't get that sort of signal, then we don't really know if things are working, if we're actually building the moat that we assume that we are. And so, these are all the challenges that we are really hoping to address with the system that we're working on. I'm going to hand it back over to Sam to discuss that.
Thanks, Mike. So yeah, let's talk about testing detections. And so before I was getting into security, getting to have all this fun hacking things, I put in a lot of years just as a straight up software developer. And as the devs in the audience are all too familiar with, testing, whether it's unit, end-to-end, manual QA in many cases, is a very well standardized part of the life cycle of software dev. We want to bring that same level of rigor to testing detections. We want to know that those detections are actually going to perform when we need them to, and that at any given time, we always have that level of protection that they should be providing. And the way that we want to do that, the highest fidelity way that can really give us that confidence is to simulate real attacker activity and see how the detections do. So the real issue and why this is so important to do is because the detections are at scale, are themselves these very large software products and data pipelines with a whole bunch of infrastructure dependencies and a whole bunch of things that can go wrong. And so when you try landing really complex detections, depending on complex infrastructure, there are so many different mistakes that can be made. And the thing that makes it uniquely challenging is that unlike when you make a mistake writing some endpoint as a web dev, almost always the failures are just going to be silent and you might not know anything is wrong. There's not going to be something throwing 500 errors out there to the world that is going to make some user angry and somebody's going to tell you. So we really have to take an extra degree of care to make sure that all of this stuff is always working well. So let's talk a little bit about how we do that purple teaming type exercise for C2 detections. So the easiest way is just throw up a real C2 server of some kind and generate an implant the way that an attacker would, pull that implant down and detonate it on some device within your corporate perimeter such that that traffic will traverse the sensors that a real attacker's traffic would traverse. And then generate some more signal, drive some post-exploitation TTPs through that C2 channel the way that an attacker would. And see what comes up, see what logs you get, see what detections fire or don't fire, and then act on that basis to continue to refine the model and harden those detections. So I want to shout out the good folks at Bishop Fox for making Sliver, who are also sponsoring this conference, I believe. Shout out to them. We love Sliver. It's really good for this type of use case because it's Golang. It can compile implants very easily to any platform, so we can drop them all different places within our environment, test the sensors within all those different paths, and it just has a nice API with Golang client that one can just use, so you can just write Go in order to automate very complex attack scenarios. So we're big fans of that, fully open source, so you can spin up as many of these as you want, no licensing headaches, and it's just real smooth to get set up and use. So shout out to them, we really like this, and yeah, we use this for a whole bunch of stuff. So what this looks like in practice, usually, is just a couple of cloud resources. Basically, you're spinning up whatever you need to do that particular type of C2 transport. So maybe I just need some domain, some TLS certs, and then the C2 itself. And all of this stuff can be automated really efficiently. So you can use all the cloud native infrastructure as code automation, Terraform. We like TerraGrunt, which is a little bit extra on top of Terraform. It's really cool. Y'all should check it out. And then we've been building up a whole bunch of code around this to basically turn this into like a command. You just run one command and all this stuff comes up and you do the test. So I want to call out specifically why we're using the word ephemeral here. So the nice thing about using this type of cloud native automation to drive the test for these detections is that you can spin up a machine. That machine comes from a AMI, if you will, a virtual machine image in the cloud that is always constantly rebuilt and fully patched, does what it's supposed to do, gets spun down. There's no footprint out there of a C2 server that's connected somehow to your internal network that then, one has certain sometimes strenuous responsibilities to keep that thing patched, make sure everything is legit there. It's comes up, does what it's supposed to do, comes down. Low operational overhead for the team so you can focus on the goal of securing the company. So we've been building this out for quite some time, and the vision here is really to get everything automated end to end. So you do these C2 tests that get spun up in the cloud, you drive the TTPs as the attacker would, you get that signal, and then you check that that alert actually came up. That's what gives you the confidence that my detections are reliable. Nobody broke them by pushing some bad code that just dropped some field and destroyed the whole pipeline. We are consistently protected from a wide variety of threats, and we can speak to how that was rigorously validated. So we're basically involved in building out all these different arrows right now, and this is going to give us that confidence. So we are in the process of getting this stuff open sourced, hopefully. And so please stay tuned. We do want to talk more about this in the near future. So I'm gonna hand this back over to Mike. Mike's gonna tell you about, on the detection side, all the cool things we've learned by repeatedly going through this process of rigorous testing.
Cool. Yeah, let's look at some data, see what this actually looks like. So I want to remind you of what our very obfuscated and not real query looks like, but the idea is that when we're targeting this SSL beaconing, this is probably a somewhere between 100 to 200 line SQL query to get all of the numbers right where we need them. And I want to show you the first bug that we encountered when we were running the system. So keep this in the front of your mind, and then let me show you the block of code that was broken. And so these 4 lines, which are just specifying which perimeter we're looking at and what the host name is what broke. On our very first test, I spent about an hour digging through the logs trying to figure out why the hell didn't this thing fire. It turns out that our attribution pipeline, which maps our IP addresses to host names, failed in this very specific instance for whatever reason, very silently, as Sam said it would. And so in this case, I completely missed the traffic, and all I needed to do was remove this host name is not null line to see that traffic. So this is an example of an extremely small thing that you might not ever think to test, and yet can have a massive impact on your ability to detect these sorts of things. The second one, going back to the loud corporate networks, lots of noise for every detector. So once I did remove that parameter, we saw 68 results, and it was cool to see Sam Manzer's laptop on there, proof that the logic itself actually works. But in addition to writing the detections, I also hand alerts off to the on-call on my team before we escalate it out further. And if I hand that person 68 alerts every day, he's going to think I'm a huge pain in the ass, and it's not going to be a good time for us. So it's really our goal to wean this number down as small as we possibly can. And to do that, we need to come up with sort of clever patterns to look for to rule out the obvious. And so the first one of those that I identified after digging through this data was, holy cow, this is how many events that we saw going to workwithincreasedintensity.com from Sam's laptop over that week. 0, 0, 0, all of a sudden a lot, and then 0 again. And so I'm thinking, okay, that's probably a reproducible pattern. If somebody's laptop gets popped inside of our corporate environment, it will quite suddenly begin making relatively high volumes of queries to some domain that we are unfamiliar with. So we can probably incorporate that logic and combine it with the beaconing logic to see if it gets us anywhere. Looking at the spikes alone, just the number of events going out to SSL domains, was also quite loud. I just want to give you a little example. This list gets much longer, but as you can see, work with increased intensity was near the top, not quite at the top. But still, we're thinking that combining this with the beaconing logic itself should be able to whittle down our results to as few as possible. It's very unlikely that drivesafemadison.com, while it was very new and random in that day, is also exhibiting the repetitive periodic beaconing traffic that we're looking for. So that's exactly what I did. I took that big long query and I added this little clause in there to say, okay, we want everything that's actually beaconing out, and we want things that are not high prevalence, essentially. Things that no more than, I think in this case, 10 clients we're connecting to. It's likely going to be much less, but just to give us some breathing room. So this is actually a third parameter that we can add into this. So now we have the beaconing logic itself, the sudden spike in traffic outgoing to this external endpoint, and low prevalence. So very few people connecting to it. Putting together all three of those pieces into the same query got us down to 8 results, which is awesome. All of a sudden, we dropped from 68, I think, or 67 to 8, which is still not quite perfect. Ideally, I only want Sam Manzer's result to be in this, and so I can hand off a single true positive. But that's not the ideal world we live in, but we continue to iterate on. The point that I really want to get across here is that the more effort we put into this sort of repetitive tuning and validation process using live emulated attacker data, the closer and closer we can get to these super high fidelity detectors relying only on the network data. Something that's particularly cool about using this approach to catch attacker behavior is that it is completely generalizable. And what I mean by that is periodic beaconing looks the same whether it's Sliver or Mythic or I don't know. Sam would have to give me the long list of commodity malwares they have at their disposal, but it all looks the same to me. It's just periodic beaconing over the same protocol analyzer to the same random and new endpoints. And so by putting all of this logic together, we can end up with these high fidelity detectors that work across the whole fleet, independent of the device that is popped and independent of the malware that's being used. And so this is what really excites me about this system, and it's sort of what I just explained, but as we were working through this process and iterating through the detection development, I essentially had a big table with all of these parameters that we're using to tune the detector and a list of trials, 1, 2, 3, 4, 5, so on, and these are the parameter values we're using. And you can actually calculate, okay, given these parameters, how many true positives were generated, aka did we catch Sam's traffic, how many false positives were generated, what's all the rest of it, all the noise. And what you're left with there is a fairly simple optimization problem. How can we minimize the number of output results given the parameters that we have here? And so with this fully automated system, this end-to-end emulated attacker traffic into my defensive detections framework, we can essentially have our detectors become self-tuning in a way with base logic and a well-defined set of tunable parameters. The entire process, can fade into the background, letting us detection engineers focus on the cool stuff, developing new detection ideas and working on new queries and adding them to this test queue. And so we're really excited to continue iterating on this and getting there. That's most of the meat of the talk. I just want to leave you guys with a couple of bits of food for thought. The first one that I really want to drive home is, as the network threat detection guy, network telemetry is awesome. It adds a lot of value to proactive detections, and don't write it off just because things are encrypted or it's a little hard to get the passive taps set up. We really have seen a lot of success and oftentimes beat the application and host level logging guys to the punch. The second one, and I think this is fairly obvious at this point, but these detectors must be continuously validated over and over again. Network behaviors shift, the entire environment is incredibly dynamic, so continuously detecting these, continuously testing these detectors is absolutely essential, so you can continue to tune parameters and have the tightest possible detection. Third one is, because all of this can be automated, it should. Again, to allow all of us security engineers to do the cool and exciting and important work of advancing the state of what we can actually detect, working on new query logic, working on new pipeline systems, so on and so forth. That's about it for our talk. I really appreciate you guys all coming out, and I guess we can open up the room for questions.
So when you say it should be automated, doesn't that cry out for some kind of machine learning approach to figuring out what the parameters should be? The constantly changing parameters.
Yeah, I think what I realized going through this process, that last slide that I was talking about where I was defining the table and working through the optimization problem, I had this moment of like, I think I'm kind of just doing machine learning by hand right now. I think the word itself gets a lot of hype to introduce AI into these systems, but it really is just statistical minimization and optimization problems. So yes, when this thing is fully automated, we could probably call it to some degree machine learning, but it really is just sort of solving that same minimize the number of alerts given the parameters that we're providing.
Another question.
Yeah.
Did you consider using Security Onion, which has a lot of the bits of the stack that you already manually created?
I did not. I inherited the tech stack that we have, but we'll check that out. Sounds interesting.
Wanted to shout out one thing real quick before we hit the next questions. We emphasize automation here a lot. There's all kinds of cool stuff that one can do with that, and would love to talk about that with anybody who's interested. But I did want to add one thing, which is if y'all don't have a lot of folks in your org who sling Terraform or do these other things, just spin up a cloud instance and give this a try manually. You get like a lot of value, and it's that first test will tell you a lot.
Yeah, so we have, I don't know the exact number, but quite a few dozen bare metal hosts that run both Zeek and Suricata. The proactive detections that I'm talking about exclusively query the Zeek data, but we also compile the Suricata data in for more kind of signature-based stuff. Ideally, we put all of the pieces of the puzzle together and query it all together, but we've had pretty good success just ingesting the Zeek data alone. It's actually just an optical tap. So the light going through the wire just gets split, and we see everything as it should be. Yep. We were hoping, well, everyone else was hoping only SAMs were genuine. I'm always hoping for a little bit more fun with all the queries. In that specific case, everything else seemed benign, though.
Yeah, they will if we have anything to say about it. I think you're absolutely right. A lot of the attack simulation stuff out there is very Windows endpoint focused, and it's really good at that. And that's really great work that those folks have done. And I think it'll be neat in the future. Like right now is kind of an exciting time for that, for this area, because with these Purple Team attack simulation efforts that we're doing, and a lot of good folks at other companies are doing too, we're starting to push into these other realms. And network is definitely a big focus for us that we want to continue.
Cool.
All right, that looks like all of them. Thank you, folks.